Okay, so this is one of the examples I'm going to show you involving the coefficient of friction. I've typed it out just in case you want to freeze frame it and then have a go at it yourself, but I'm about to read out the question to you. I've just put my glasses on so I can read it properly because I'm not wearing my contacts today. What I'm going to do is I'm going to stand behind the phone so you can hear me a bit better. The diagram shows a body of mass 15 kilograms lying initially at rest on a rough horizontal ground. The coefficient of friction between the body and the ground is 0.7. A force of 80 newtons is applied to the body as shown. Draw a fully labelled and complete force diagram. Now you might wonder why this question is there when a diagram has been drawn for you. The reason is it's not a fully complete labelled force diagram. It's just a diagram showing you a gist, a good idea of what's going on. You've just got to put on all the other forces and things going on. So there's the particle, there's the object, 15 kilograms. Of course that means there's going to be a weight force acting vertically downwards. Let's put that in. And that's going to be 15G, isn't it? And of course in the opposite direction to the direction of motion is going to be the normal reaction force. Okay? Remember, the normal reaction is always at right angles to the surface on which it's resting. Okay? So there we go. Any other forces? Well, of course, the 80 Newton force is labelled there already with the angle 50 degrees. And we have to assume then that the object, if it's going to move, is going to move that way towards the right. I usually find it's a good idea to put in an acceleration arrow showing you the direction of motion. And then there's the frictional force. Friction will oppose the direction of motion. So it's going to be the other way towards the left. I'm going to put it in there like that. Be careful, we often use F for friction, just as we use F in F equals ma. They mean slightly different things. F in F equals ma is the total resolved force in a particular direction. F here is the frictional force itself. All right? That's a fully labelled force diagram. Let's answer part B. Find the magnitude of the normal reaction force. So find out what R is. For this, we've got to resolve vertically. We've got to resolve vertically. Now choose a direction as being positive. I normally choose upwards as being positive myself. So we've got R is positive. Any other upwards forces? Of course. There's the 80 Newton force. And we've got to split this into a horizontal and vertical component. If you draw a right angle triangle like this, then you can see 80 newtons. That's the actual direction of the force, but split horizontally and vertically, it's this component here that you want. And using the right angle triangle and trigonometry, it's going to be 80 newtons multiplied by the sine of 50 degrees, because this side here is opposite the angle 50 degrees. So positive, so it's plus 80 sine 50 degrees. And then opposite that is 15G, okay, vertically downwards. Now you can say equals 15G. I'm going to because I'm running out of space, if I'm honest. Okay? But the fact of the matter is, it's not moving vertically, so the acceleration is 0, so all the forces must balance out. Total force resolved vertically must be 0, all right? So what we're saying is those two forces combined, those two upwards forces must balance out with that one there. This is enough for us to work out what our value of R is. Hold on a minute, I've got to get my calculator. Talk to yourself while I'm getting my calculator. Yeah, here I am. Sorry for not having one in my pocket. All right. So let's work out what R is going to be. So it's going to be 15 times 9.8, so 15G, 147, subtract 80, and this is when I realised my calculator's in radians mode. Of course it's in radians mode. Which other mode would it be in? Because radians is the preferred. Let's start again. 15 times 9.8, okay, 147, subtract 80 sine 50 degrees. All right? And that gives me, gives me 85.7. So let's put it as 86 newtons to two significant figures, shall we? Yeah. So that's the magnitude of the normal reaction force. Now, before we go any further, we can at this stage work out the frictional force F, using F equals mu R, can't we? So we've got F equals mu R as our formula between friction and the normal reaction force. 0.7 is the value of mu. So you've got F equals 0.7 multiplied by R. So let's, before I reset this calculator, let's just work out 0.7 of that. So multiplied by 0.7. And that's proof that I am actually in a school. I mean, which other buildings have bells like that? Seriously. Yeah. So the frictional force ought to be 60 newtons. Now let's just make sure we're aware of what that means. The maximum possible frictional force available between surface and object is 60 newtons. Okay. Now what we got to decide is, in answering part C, we got to decide whether this force horizontally is enough to make the object move. If horizontally the force is above this figure here, then it's going to move. The reason is because the pulling force is going to be greater than the resistive force, the frictional force. However, if this pulling force is not enough, if it's less than 60, then that's not going to be sufficient. It's not going to move. If it's precisely that, as in 60.0, well, yeah, then it will be in limited equilibrium. The question is, state whether the body will remain at rest or accelerate along the ground. So let's just work out what this is, resolving horizontally. This is going to be 80 multiplied by cosine 50 degrees, because cosine is adjacent to 50. So 80 cosine 50 degrees. Let's just spell cos correctly, shall we? COS. So 80 cos 50 degrees. So again, now my calculator's in degrees mode, I can do it. That's a reminder, by the way, when you are doing mechanics, make sure it's in degrees mode, because if you've just switched from pure maths, for example, where I've been doing trigonometry, you're normally in radians mode, aren't you? That gives me 51.4. Yeah, 50. Let's round it to 51 newtons to be consistent with that. Okay, I've given both of them to two significant figures. All right. So here you can see, I hope, that this pulling force here is 51 newtons. This maximum resistive force, the frictional force we call it here, is 60 newtons. Therefore, this is not going to be enough. In reality, of course, the surface will generate enough friction so that it can't move. All right. So what it's going to do is it's going to actually be exactly the same as that. Okay, because obviously the frictional force is never going to be greater than this pulling force. It's not going to move on its own. You know, it's not Yoda with the force. It's not actually going to move on its own. All right. But yeah, but it does actually show you that the object is going to remain at rest. It will not accelerate. Okay. I'm hoping you understood that. I'm hoping that example was helpful to you. All right. Okay, this is my next example. Let me just read it to you. Okay. So a box of mass 5 kilograms lies on rough horizontal floor. The coefficient of friction between the box and the ground is 0.5. A force P is applied at an angle alpha above the horizontal to the box to pull it horizontally along the floor. Given that tan alpha is 0.75, find the magnitude of P which is necessary to achieve this. All right. So there's a lot of things going on there, isn't there? And that's what makes it challenging in terms of a mechanics question. It's a full-on paragraph, isn't it? You've got to read that, you've got to dissect that, you've got to fully understand exactly what it means. Where's a good starting place? I'm hoping you're thinking force diagram. Yes, draw a force diagram. Maybe pause the video and then unpause it when you're ready. Okay? Here is my force diagram. There we go. So let's start off with the object itself. Box of mass 5 kilograms, so clearly the weight is going to be 5g vertically downwards. It's on a horizontal surface, it's moving horizontally, therefore normal reaction is going to be at right angles to the horizontal surface, so vertically upwards. Good so far? Hope so. And then P, a force P is applied at an angle of alpha above the horizontal. Because it's above the horizontal, it's like this, an angle of inclination. Okay, it's going to be above, and we don't know what alpha is, but we'll come back to that in a minute. Then, if it does move, we're going to assume that it's going to move this way. Okay. Again, I'll talk to that about that in 1 minute as well. If it's on the point of moving that way, the frictional force will be opposing it. It will be this way. So that's a fully labelled force diagram. Right. A couple of things. Right. In reverse order, A. it says find the magnitude of P which is necessary for it to start moving. Necessary for it to start moving. Okay. Let's go bananas. If P was, say, 1,000,000 newtons, it's not, of course, but that's quite a lot. If P was, say, 1,000,000 newtons, of course it's going to move. Okay. If it's 100,000 newtons, of course it's going to move. Okay. What about if P was 100 newtons? What if it's 50 newtons? What if it's 30 newtons? You don't know, do you? Okay. What we're looking for is what is the minimum value of P required for it to start moving. If you think about it, it's going to happen when the object is in what's called a limiting equilibrium, on the point of moving. When it's on the point of moving, at that exact instant, the acceleration is 0. All right? The acceleration is going to be 0. Let's put some units in there as well. So what we're going to do is, when we're resolving horizontally using F equals ma, just remember to use A is equal to 0 for this. Right, the other thing, we're not actually given a value of alpha. We're told that, there it is, tan alpha is 0.75. I suggest you write it as a fraction. You might be thinking, why as a fraction? Well, the answer is quite simple. When you're resolving horizontally and vertically, you're going to be using sine alpha and cosine alpha. So you don't really need to work out a value of alpha, as long as you've got an expression for sine alpha and cosine alpha. And we can get it if you consider tan alpha is 3/4, and if you consider also what that looks like in terms of a right angled triangle. So if that's alpha, tan alpha is opposite over adjacent. So if you use opposite as 3, adjacent as 4, and then complete it, the 3, 4, 5 triangle, Pythagorean triple, we can get an expression for cosine alpha and sine alpha. Cosine alpha is going to be adjacent over hypotenuse, 4/5, and sine alpha is going to be opposite over hypotenuse, which is 3/5. Okay. Also, we're given the coefficient of friction, mu is 0.5. So let me just take a step back. So you've got all that information there that you are going to have to use to answer the question. That's why it's challenging. That is why it's challenging. You've got to take a paragraph like this, you've got to be able to draw a force diagram, you've got to be able to, well, obviously note that, it's probably the easy bit, and you've got to be able to get expression for sine alpha and cosine alpha, okay, before you actually get going in answering the question. Are you ready to get going? So am I. Let's go. Next page then. This is the beauty of my interactive whiteboard, you see. So far, in summary, I've got this here for you, just to recap of what we've got earlier. And what we've got to do next is resolve horizontally and vertically. All right? So in terms of the diagram, this is what it's going to be horizontally for the force P, P cosine alpha, and for the vertical component, it's going to be P sine alpha. You can see that from the right angle triangle that I've drawn. Horizontally, an equation for that. Maybe think about it and then pause the video. Unpause it when you're ready, but I'm not going to give you too much time. Hope you're quick with the old pause there. So here we go, P cosine alpha minus F equals 0. Just do remember what I said about the acceleration. What we've got to consider is the maximum value of, the maximum value of the frictional force that can be generated is going to be when the object is on the point of moving, then after it's moving, it will continue to generate that amount. That's what we mean by F in the F equals mu r equation. And we're looking for what's the minimum value of P possible. And that's going to happen when the object is on the point of moving. Limiting equilibrium is called A is equal to 0. So in our equations, F equals ma, we have got A is equal to 0, you see. So the total resolved force horizontally, P cosine alpha, subtract F, because they're in opposite directions, is equal to 0. And let's see what we can do with that. We can then write it as 4/5 P minus 0.5 R equals 0. You happy with that? Well, F, of course, I've written over here, is 0.5 R using F equals mu R. And notice how we can put in the cosine alpha there. Cosine alpha is 4/5. So we've got 4/5 of P. All right? And then we've got 8/5 of P minus R equals 0. I just decided to multiply by 2 there because it's easier when you don't have fractions or as many fractions. It's easier when you've got as few fractions as possible. And we can't really get any further than that because we've got 2 unknowns, haven't we? Now at this stage, okay, you might think, oh, I'm stuck. Let's have a go at this. but when you've done a few of them, you get the idea that there's got to be simultaneous equations. You've probably seen that a lot in mechanics, haven't you? Simultaneous equations happens with some of the SUVAT questions as well, when you've got two objects that are moving, okay? Simultaneous equations is a major aspect, shall we say, of solving mechanics problems. Right? So I'm going to write r equals 8/5 p, because guaranteed I'm going to get another equation involving r and p, and I'm going to have to make a substitution here. Okay, so let's have a look at vertically. Well, vertically, what have we got? We've got r. I always take upwards as being positive, by the way. And then the vertical component of p, which is p sine alpha. So r plus p sine alpha. And then opposing that is the weight downwards, minus 5g. And of course, the acceleration vertically is 0 as well, because it's not moving at all vertically. And then let's see what we can do with that. So we've got r, and then 3/5 p, making use of sine alpha is 3/5 minus 5g equals 0. And then you can see that I put in blue the helpful note there. This is when you can substitute r, you see. And you substitute r in place of that. So you've got 8/5 p plus 3/5 p minus 5g. That's great, because now you've got an equation with one unknown. You can now solve it and work out that value of p. And answer the question, what is the value of p that's needed for this thing to start moving? Okay. So solving it, here's the next line of working, and then you should end up with P is 22.3 newtons. Okay, 22.3 newtons. So what that means is, as a reminder, when P is a force of 22.3 newtons, then this is on the point of slipping. It's on the point of slipping that way. It's on the point of moving. It's what we call limited equilibrium. But if you make it greater than 22.3, if it's say 23 or 24 or 25, any number that's greater than that, then it's going to be moving, okay? So in answering the question, what is the smallest value of P such that it's going to move, it is 22.3 newtons, okay? I'm hoping that you found that useful and interesting, okay? I'll see you again.